Okay, welcome back everyone. The point of today's video is to understand what we mean by sigma notation. And sigma is we often use for sigma this big Greek letter, sigma, which kind of looks like a big pointy S. And as always in these lectures, the point is not necessarily to bombard you with computations or to judge you on right or wrong answers, but simply to demystify and explain notation, which might otherwise be mystifying. So what we're going to do in this lecture is just work through 3 examples. Each one of them is an example of sigma notation. Each one of these things here, the sum from I equals 1 to 4 of I squared, the sum from I equals 1 to 5 of 2i plus 3, and the sum from j equals 3 to 7 of j over 2. These are all just fancy ways of writing numbers. In fact, to tell you the answer in advance, this first number equals 30, the second number equals 45, and this last number equals 25 halves. How on earth did I know that? The point of this lecture is to learn why that's true. Let's dive in, do the first one. We're going to compute the sum from I equals 1 to 4 of I squared. What I'm going to do is just do this myself first, and then walk you through and unpack how I did that. Okay, so the sum from I equals 1 to 4 of I squared is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay, so suppose someone paid me to do this problem. I consider myself done. I've worked it out. I've translated it from sigma notation to something someone who knows arithmetic could do. If that person's really a stickler for details, so they're going to say, well, keep going. And then I'm going to say, maybe you need to pay me more money. And after we're done with that negotiation, I'm going to say, okay, from here it's arithmetic. This is just equal to ... The dot's covering up the fact that I've done this in advance. This is equal to 30, which is the answer we saw before. But the real point of today's lecture is to understand this first equal sign. How on earth did I know that this funny symbol, the sum from I equals 1 to 4 of I squared, was equal to 1 squared plus 2 squared plus 3 squared plus 4 squared? Okay, so let's walk through that. The first thing to realize looking at this symbol is there's a bunch of things. First, there's a counter in here. There's a symbol in here, I squared. That same person walks me up to me on the street, person's pretty annoying by now, and says, I'll give you $10 if you tell me what I squared is. No deal. It's not really a fair question. I don't know what I is. But actually I have some hints. Down here at the bottom, I know how to start my range of I. I know that I should start from I equals 1. And at the top, I know that I should finish when I is 4. Okay, so let's do some scratch work and work that out on the side. Here I have I equals 1. Here I have I equals 2. Here I have I equals 3. And here I have I equals 4. So you'll notice that starting range, starting from 1, that finishing range ending at 4. Now actually there's something here that's a little unfair. Nothing in the symbol tells me that I count by 1, going from the bottom of my range to the top of my range. That's okay, that's sort of a cultural agreement. You start from the low I, you end at the top I, and you count by 1. Okay, fine, so what do? To each one of these I's, we do what this thing in the middle tells us to do. In this case, that thing in the middle, very bossy, tells us to square I. So if I equals 1, then I squared equals 1 squared. If I equals 2, then I squared equals 2 squared. If I equals 3, then I squared equals 3 squared. I think you get the hang of it. If I equals 4, then I squared equals 4 squared. Okay, we've done the scratch work on the side. What do we do next? Well, sigma, what you want to think about this, is equal to sum. Meaning, we take all of these answers here and we add them up. And that's how we get what we get up here. We've computed on the side that when I equals 1, I squared equals 1 squared, and so on, and then we add them all up and we get our answer. For those of you who are sort of business-minded, you can think of this as a process which can be broken up into parallel processes undertaken by different workers. So one worker can compute what happens when I equals 1, one worker can do when I equals 2, one when I equals 3, one when I equals 4. It doesn't really matter when they do them. You can do them at the same time in parallel. At the end of the day, they compare their answers. The last worker adds them all up, and we get the answer that we get over here or over here. Okay, fine. Let's do another example. Very much like the same, a little bit of a twist. So the second promised example is the sum from I equals 1 to 5 of 2i plus 3. Only thing that changed from last time is we changed the top of the range, and we changed the thing inside. So just like before, let's do it one more time in full detail. I go from I equals 1, I equals 2, I equals 3, I equals 4, and I equals 5. What do I do to I equals 1? I do what I'm told to do to any I by this symbol. So in this case, I take it, I multiply it by 2, and then I add 3. Here I get 2 times 1 plus 3. Here I get 2 times 2 plus 3. Here I get 2 times 3 plus 3. Here I get 2 times 4 plus 3. And here I get 2 times 5 plus 3. End of the day, take them all up, add them up, just like we did before. So we do that up here. This is equal to 2 times 1 plus 3 plus 2 times 2 plus 3. And you notice this is getting a little tedious. That's sort of the point. Adding up long strings of numbers is tedious. Really, the added value here is that the sigma notation gives you a compact way of representing the work order. This is what you're going to have to do should you choose to do it. Maybe you won't choose to do it. And then we have 2 times 5 plus 3. And again, we're really done. I consider myself done. If you really want an answer, you want to pay me a little bit more money, maybe I've done this work in advance. Turns out this is equal to 45, which we already knew because I told you at the beginning, but maybe you believed me, maybe you didn't. Okay, fine. Let's do one more example. In this case, we're going to break the idea that you have to start from 1 with the counter. We're also going to break the idea that you have to use I. Let's take the sum from j equals 3 to 7 of j over 2. You know what? We're going to be big kids about this now and not even do our little scratch work because I think we get the idea. This tells us to do something to j. What do we do to j? We divide it by 2. Okay, boss, but which j's do we do that to? We do it from j equals 3, incrementing 1 up to j equals 7. Okay, so this is equal to 3 over 2, plus 4 over 2, plus 5 over 2, plus 6 over 2, plus 7 over 2. We work all that out. I really don't like arithmetic and I really don't like fractions, so here I'm going to be up front and say I did this myself at home, actually at 5 in the morning. This is equal to 25 divided by 2. Okay, so those were 3 easy examples. Now I'm going to give you the 100 gold coins gold star problem, which is I want you to compute the sum from r equals 3 to 7 of r over 2. I want you to pause the video and think about this. Okay, so there's 2 ways to have done this. One is to do it directly, just as we did before. The other is to be a little bit clever and say, nah, it's a trick question. It's really just 25 over 2. How come? Well, the only difference is between these two is one's got a j, one's got an r. Otherwise, it's the same range of j, same range of r, and the same thing is being done to j and r. There's nothing special about j and r. In fact, j and r are examples of something we call dummy indices. And we mean to be as super disrespectful as dummy makes it sound. J and R, you dummies, are not real variables. They're not real unknowns like in algebra when you solve 2x plus 1 equals 8 and you have to solve for x and you either get points or not. They don't have any independent existence. There's no answer to what they are. They're just symbols for counters. They say start at something equals 3, increment that something up to 7, do the following to something. To really drive that point home, note that the sum from smiley face equals 3 to 7 of smiley face over 2. What do you think that is? Well, it's just 25 halves too. There's nothing special about it. That said, let's not get too wild. There's generally a cultural agreement that when we use dummy indices, we tend to use symbols like I, J, K, maybe L, maybe R, sometimes M, sometimes N. In other words, we tend to use things from around the middle of the alphabet. But that's just an agreement. No particular reason you couldn't use a B, smiley face, maybe try to draw a little doggy. It's really very, very poorly because that's not what I do. Ears. People will look at you funny, but you'd be just as perfectly right.